Hello, statistics student. This video is for chapter 7.1, central limit theorem for sample mean. So a brief explanation of what is sampling distribution, and because that's what central limit theorem is about, and what is sampling distribution of sample mean. We know what a distribution of x is. So if I have a lot of data measuring height or measuring commute time or measuring income, so that individual x you look down the value and then you make a distribution. So this could be done by an histogram or dot plot. So anyway, we view suppose if the distribution is x is normal, then I collect a sample from it. So there's a lot of x data here. So I would just say, oh, these are x around here. I'm going to randomly collect them, pick those up, and there is one sample. Oh, no, this is just x, right? So there's a lot of x. And I from all these x sample size n, and I calculate an x bar, right? So I can repeat this and calculate another x bar with different or just randomly select from the same pool of the population. Remember, a sample is a smaller subset of it, so your x bar would not be the same as mu. But how would x bar distribute? So they would, I think we all agree that x bar varies. So sometimes it's higher, sometimes it's lower. Um, it would not exactly equal to population distribution. So we have all these X bar that we collect. If we continue to do that, later on I'll run a demo where actually I'll do a lot of X bar and then we'll figure out what the distribution of X bar is. So it turns out that the distribution of X bar is always normal for all sample size n. So if your sample size is 10 or 20 or 30, it would be normal. And of course, the normal distribution would be different for different sample size. Central limit theorem talks about how different they are, what is the mean of this new distribution of X bar, and what is the standard deviation. So we call this process of doing a sample distribution of sample mean, or actually a distribution of sample mean, we call it sampling distribution. So it's just very intuitive to say, well, you started with x is normal, your x bar should be normal. So they will x bar will spread out in different direction. What happens if x bar is not? So look at this diagram. Amazingly, if you have a population that is not normal, like in this one, irregular shape, and actually it can be any shape. It could be uniform, it could be left skew or right skew. But if you collect a sample size, same sample size n, it has to be the same one, right? And then you distribute them. It turns out that it is normal. X bar is always normal no matter what you start with. So that's why we study in chapter 6, we study so long on normal distribution. In real life, actually, normal distribution is not easy to come by. But if you do X bar, they're always normal. And the mean of this new distribution is the same as the original mean. Well, mu might not be in the middle. It could be any place. It would be closer to the end, maybe, I think, with a sigma that you can calculate. But then this new normal with the X bar sampling distribution has a standard deviation of sigma over square root n. This theorem is determined by the central limit theorem. So let's look at the central limit theorem. The theorem says for all samples of same size n with n greater than 30, if sample size is greater than 30, and the sampling distribution of x bar can be approximated by normal distribution with mean mu and standard deviation sigma over square root n. The original mean is mu. The original standard deviation is sigma over square root n. No matter what distribution you have, x bar is normally distributed, and actually you can calculate the standard deviation. So here note, this applies to all distribution of x. So even x has a left skew, right skew, it works. But if x is normally distributed, you do not need n greater than 30 requirement. So any distribution, any n would work. So when you do, and the second thing is to be careful is this, your sample has to be a simple random sample. It cannot be a biased sample. So you can analyze a random sample and know how x bar distribute. In a nutshell, the central limit theorem say mu of x bar is mu, sigma of x bar is sigma over square root n, and then the distribution of x bar is normal. Okay, distribution of x bar is normal. So some people write like this: x bar distribution is roughly normal by the big N with mu sigma over square root n. Oh, also when we say sigma of x bar, that means the sampling distribution of x bar standard deviation. Sometimes we don't call it standard deviation to distinguish it from the original sigma, and there is another term for it. So it's sometimes in some software and actually in some book they call it standard error. So there's another name for this. So this particular behavior that is really surprising, right? You start with any distribution, you just do a lot of x bar. It turns out you have a normal distribution. So this can be illustrated in a normal demo. So there is a sampling distribution simulation demo. So if I have a population that is normally distributed and I pick a sample size of 10, say for example, and I collect 1,000 sample, the mean is normal. Okay, and then if I maybe we can try what would other things be? So we can say so this is the mean standard deviation. This is not very normal, but this is normal. We can say median. Would median be normal? Okay, so we can do 10,000 times. Mean is normal. Median in this case is quite normal. Okay, but it's not. You cannot predict how they distribute. So for central limit theorem, you can predict the means distribution. But if it is not normal, so say you can draw any distribution like that. Yeah, maybe we'll just make a very weird distribution. And then I would do a big sample size, bigger, maybe 25. And I do 10,000 times. So look what happened. The mean is normal, but median is not. Okay, when you have these kind. So central limit theorem apply to anything, any distribution. Your sample mean, distribution of mean is normal. And if n is greater than 30, is you can predict the values of the mean and standard deviation. Okay, let's move on to doing work problems. So the problem that we want to work on is about a standardized test. So everybody knows standardized test has normal distribution. The mean is 150 and the standard deviation is 18. So this is X, standardized test scores. Each individual score is X and it is normal. Is normal 150 and 18. Right this way. But then you collect you have 20 students to take the test, and then you calculate the mean score x bar of the 20 students. So we are asking if the distribution of the mean score of 20 students normally distributed. It is yes. We don't have to worry about the sample size less than 30 because the original distribution is already normally distributed. So it is guaranteed to be normal. So because original score is normal. Okay, so let's look at this B part. And because of that, we would have two normal distribution, right? One is the original one and one is the new one. So B is, what is the mean and standard deviation of X bar? So X bar distributed also normally, and the mu of X bar is still 150, right? And the sigma of X bar is sigma over square root n, right? Sigma over square root n, that is it 18 over square root of 20? And in the calculator, I already calculated, the scientific calculator is 4.0249. So do more decimal places. Now we have two probability question to answer. C. Find the probability that a student, so this is about X, score is greater than 160. So we would write 150 with sigma equal to 18 here. You use the online calculator to find probability. You will use the online calculator just from stat book, and it's 150, 18, right? and then we want it to be above 160, more than 160, we calculate 0.2893. Oh, wrong one. Where is my 7.1? Yeah, 0.2893. So we say x, oh yeah, 160 is actually not even one tick mark away, so you know that it's quite large. The probability is quite large. 0.2893, right? Then we also you want to use the same thing to calculate the probability the mean score, not x, but mean score of 20 students is greater than 160. So I'll draw the normal. It's still 150, but sigma now is 4.0249, right? So each tick mark is much smaller now, and to be able to above 160, that is actually more than 2 standard deviation away. So I can graph it here. So probability of x greater than 160. Again, I will employ the same calculator, normal calculator, but I have to change the standard deviation to 4.0249. And then above 160, they still ask us this 0.0065. So this is 0.0065. So that means less than 1%, right? 1, 2 is 0.7%. The last one is 28%. So you can see that this is much narrower. In the picture, we write it as if it's the same shape, the same normal shape, but actually it's a little different. Okay, so we will do another example in the next video. Okay, so basically this is what you do. You just do distribution of x bar. I think maybe I can finish this. So this one. Coke can are filled so that the actual amount have a mean of 12 ounces and standard deviation is 0.11. Okay, so this is x, right? Each can of Coke is x. Is normally distributed with 12 and then 0.11. And then they will ask, is the distribution of mean amount of 36 can, n is 36. Normally distributed? Yes, because n is greater than 30. I don't even know if they're normally distributed, but I can guarantee that CRT, central limit theorems guarantee that x bar will be normally distributed, and x bar would have a normal distribution of 12 and then 0.11 divided by square root of 36. That means divided by 6, right? What is the mean and standard deviation? So that's what we talk about. Find the percent of individual Coke with amount between 11.9 to 12.1. So use the normal calculator. 12. Oh, is it 12? What was it? 12 ons because it's 12 on 0.11. So this is 0.11. We want it to be between two value. What? 11.9 and 12.1. 11.9 and 12.1. That means just 1 ounce, 0.1 ounce away, so it's in the middle. 0.6367. So we'll say it is probability of x is between 11.9 and 12.1 is 0.6367. So it's 63%. Oh, we have to do it in percent because they asked for percent. 63.67%. What about the mean amount of 36 Coke? So that means x bar. So this is x bar now. Okay, so not x. So x bar would be, we do the same thing, 11.9, but x bar is between 12.1 and that. So let's find out what is 11.11 divided by 6. It's 0.0183. So sigma is 0.0183. So we can quickly go over that. This is the same, but 0.0183 and recalculate. So it is 100%. So we say it's 100%. So last one, income are known to have a distribution of this